Professor Dr. Jaydev Dinda.
Dr. Dinda is the Director of R&D and the Professor of Chemistry at Utkal University, Bhubaneswar. He has received a Fellowship of Ministry of Education and Culture, Spain 2006. Dr. Dinda has previously chaired the Chemistry Department at Haldia Institute of Technology and ITM University, Gwalior. He has published 74 plus international journal paper and supervised 8 PhD scholars. His research group achieved a breakthrough in synthesizing gold-3 N-heterocyclic carbonates and exploring their anti-cancer application. He has managed several funded projects under India's Department of Science and Technology and publishes widely in leading journals like RSC, ACS, Willy and elsewhere. I am glad to invite such a great personality to the stage. Please welcome Dr. Jaydev Dinda.
Thank you to organizer to giving me opportunity to share some of my research. I am very thankful to Abunishar, Deepa Madam and Santosh. They have given the opportunity. So today my topic basically in organometallic supramolecular chemistry, and I will share some of the some of my research very relevant to the student. Basically, third semester we have supramolecular bioorganic chemistry, and fourth semester we have organometallic chemistry. So I will share my slides, and the things mostly I did my research in my laboratory, and how it is related to the present topic I will show that. Okay. So I will operate it from my own laptop, so I will not be here. So look at the things what happen. Okay. Thank you. So look at the things we have theory paper 502, that is bioinorganic and supramolecular chemistry, that is in your syllabus, and that is the syllabus of Utkal University. Stuart Science College belong to this Utkal University, and that is the third year syllabus. Okay, fine, no problem. Before going to this my discussions, I will show some picture. Because most of the cases we got the concept from the nature. So now I am showing one picture. Look, see what. Sorry. Oh, no, that's not taking. Yeah. See, landing of a flight, how we get the conception from a bar, how the plane landed. So this is landing of a flight. We got the conception of the landing of a flight from a simple bar. So most of the cases we learned a huge from the nature. So that is why today I will see how we got the conception from the organometallic chemistry, supramolecular chemistry from the nature. Okay, fine. Before going to the topic, we have seen the simple water, which is nothing but life, and we have DNA structure. This is nothing but one supramolecular. So this supramolecular assembly teaches us how it is built up, and from the sense of supramolecular chemistry, how water important for our life, and how DNA that is a strategic planner of our life. So we can think about this one. So from this importance of this topic, I will start about this supramolecular organometallic chemistry. Okay. So if I define supramolecular organometallic chemistry is nothing but it is a chemistry beyond something, and having and mostly we are talking about importance. Later on we come the things. So importance, it is importance because of the because it is very related to life. If you look about these things, it has medical importance. You have disease diagnostics, you have cell therapy. It has semiconductor property, lot of important aspect of this field. So that is why we want to look about the supramolecular chemistry. Okay, fine. I will show some of the and if I want to say just one minute. Yeah, these are the supramolecular chemistry, how it is formed, because this is nothing but it is with the help of hydrogen bonding, metal coordination, hydrophobic interaction, van der Waals forces, pi-pi interaction, and halogen bonding. So these are the very helpful for the developing of the supramolecular chemistry. All this molecule, whatever I shown here, we have developed in our lab. So I will see how this kind of secondary interaction, non-covalent interaction is very important to develop the supramolecular chemistry. Okay. So you look about these things. If you look about the supramolecular chemistry, I can say you that this is a hydrogen bonding, metal-metal interaction, condition bonding, hydrophobic force, whatever it is, maybe everything started from a very small molecule. Okay. So think about, I am giving a physical example. Think about, I am here. So I have my parents who brings to this earth. I have a very good interaction with my parents. Later on, when I moved to my high school, this is my high school teacher and who teaches me chemistry in the secondary level. This is my PhD supervisor, this is my wife, this is my daughter, and this is my student. So if you look about these things, how single person I am interacted with each other, and I have a very good relations with everybody. But think about, I don't have the same interaction with everybody. To some extent I have a very strong interaction, may not be others. So that is why many cases you will see hydrogen bonding, pi-pi interaction and others might be different from each other. So that is why force should be different from each other. So that is the basic concept we received from the nature. Anyway, so now look about these things. To develop the hydrogen supramolecular organometallic chemistry, many of you have read that. Think about simple benzene. Benzene has a pi electron, so there is a pi-pi interaction, or better we say the pi stacking. And here we look about these things, this is benzene, and here is one hydrogen. So hydrogen pi interaction, and lot of other interaction like pi-pi interaction, CH-pi interaction, CH interaction, and metal pi interaction. Lot of interaction will help to develop the supramolecule. So now supramolecule. I am showing one simple molecule. Think about, this is a pyrazine imidazolium molecule we have developed to develop the supramolecular chemistry. We have synthesized this compound. If you look about this is the most acidic proton, and this proton appears near about 10.32 ppm. When we make the silver complex, then this proton will be disappeared and their silver carbon bond is formed. So that is why you look about we have taken the NMR because this seminar is very related to spectroscopy. So that is why we have taken the help of NMR spectroscopy to look about whether this complex is forming or not. So difference between this and this, you look about these things. Using simple one NMR, I understand that my complex is formed, because in the starting material there was proton, but in the complex there is proton is disappeared. So that simple one proton NMR tells that my complex is formed. So now I move to 13C NMR. If you look about these things, this carbon signal appears near around 143.59 ppm. When this complex is formed, that is shifted to 165. So that is why a huge shift that tells about my complex is formed. So that is with the help of the NMR we assign the complexes fine. But to know the geometry, how they are really forming, how they are bonding connectivity, we took about the help of X-ray crystallography. So you look about these things. This is simple molecule here. This simple molecule here, how this molecule develop a supramolecule here. So now I will show this is the development of the supramolecule. Okay, fine. Yeah, so it's fine. So now just 1 minute. So look at these things. Look at these things. We have synthesized this molecule in our laboratory. This is a complex having this two silver here. We have silver. If you make it, yeah, you look about the two silver, and silver is +1 oxidation state. So 2 + 1 is neutralized by 2 negative charge, that is pH6 minus. Okay, fine, no problem. So now you look about these things, interesting how cleverly you have designed this molecule, because you look about there is stored nitrogen here, in between there is hydrogen is there, and we thought this hydrogen must be very acidic hydrogen. Now I will try to develop the supramolecular chemistry using this simple molecule. Look about this, what happened. Yeah. Yeah. So just 1 minute. Yeah, I want to make the molecule very simple, and let's see. And I will show how interesting this molecule and how they are bonding to each other, and how we have I mean hydrogen bonding, pi interaction, lot of things. So now I will arrange these things looked better. Yeah. So look about these things. This looks like a, and when we this is the cavity present here. When we remove this PF6, look about these things. What things happen? Yeah. So now cavity present here. Anyway, so my point is that now from this simple molecule, I will show how they help to supramolecular chemistry. So thing is that yeah. Look at the things. Look at the things. We say pi interaction. We look about this one. This is one interaction with this another molecule. This is develop pi interaction, and we have PF6 here. You look about these things. This is fluorine. So this fluorine have interaction with this hydrogen. So that is why we have CHF hydrogen bonding, and we have pi interaction, CH pi interaction, CF interaction. Lot of interaction is there, and this interaction help to develop the supramolecule. So that is why my point is that whatever we have read in our textbook, that we have developed the chemistry, and we have synthesized this compound judiciously, and to find out whether this kind of interaction present or not. So that is a practical visualization of this molecule, and we have look about these things. This pi stacking interaction leads to a very good supramolecule. Anyway, so this is one thing I have shown to you. Anyway, so this is the supramolecular chemistry. Now I move to supramolecular chemistry. When we develop the things, we consider nitrogen, sulfur, several donors. But if you look about these things, I am telling about organometallic supramolecular chemistry. Okay, organometallic supramolecular chemistry. Okay, so organometallic supramolecular chemistry means we are trying to develop one metal carbon bonds. Now the question is there, why so important to develop a metal carbon bond? And for this synthesis of this compound, we have taken the help of N heterocyclic carbene. This is the molecule N heterocyclic carbene, because this is defined at carbene, you know, everybody you know, when this carbene carbon will attach at least one nitrogen, and this is a heterocyclic molecule. So that is why we call it N heterocyclic carbene, and there is a metal carbon bond. Now the question is that why you are interested about to develop the metal carbon bond. So I always take the help of some nature. So you look about the huge, I mean, good philosophy. It says that if you think we have taken a pigeon, if you hold the pigeon tightly, it will die. If you hold the pigeon loosely, it will fly. And if you hold these things within the limited things, it will remain for you ever. I mean, point is that if this metal carbon bond is very, not carbon, if a metal some donor bond is very strong, that have some difficulties.
If the metal carbon bond is very weak, then it is unstable. So, we have to develop such a bond, so that should be not very strong, not very weak. So, that gives the lot of chemistry, because we will try to translate this one. So, if the metal carbon bond is reasonable strength, then we can replace this metal like silver by gold, say ruthenium, palladium, platinum, like this one. So, we took this opportunity, that is why we are interested about the organometallic chemistry. So, that is why in 4th semester we have in the definition we say that organometallic compound is that one at least contain one metal carbon bond. So, most of our compound I will show in every compound there will be some metal carbon bond. So, that is the beauty, and we have utilized this metal carbon bond, and we have used the multi-topic ligand to develop the supramolecular chemistry. Okay? Fine. So, that is why look about these things, simple things before going to this one. We have developed some kind of ligand, organic molecule we have synthesized, and we have capitalized two donor center. One is carbon donor center, one is nitrogen donor center. Sometimes we have counter anion PF6, counter anion chloride, and counter anion bromide. And we will look about this thing. We change of this counter anion, the structure will be different. And at the same time, we change this position of the nitrogen. Here nitrogen is 3 position, but sometimes we put in the 2 position, and sometimes we put in 4 position. So, change in the position of this nitrogen will change the geometry, structure and property. At the same time, change with the counter anion also change the property and change the structure. So, now I will see what happened. So, look about these things. We have this organic molecule. When this organic molecule we have treated with silver oxide, and we treated that this is the we see this is the nitrogen donor, this is the carbon donor. So, when we have the silver, then we have look about these things. This is a make a great like tetranuclear silver structure. This is 1, 2, 3, 4 silver is there. And when we try to replace this silver by gold, then interesting things happen, because in transmetallization reaction we see that all the silver might be transferred, or all the silver should be substituted, but in that cases only the silver which is attached with this carbon that is selectively transmetallic. I mean this is in position of the silver, gold is coming, but what is present in case of nitrogen means what is bonded with nitrogen, that remains same. So, that is why this is a selective transformation or selective metallizations. So, this paper we have published this year in RSC, Royal Society RSC advanced paper. Okay, fine. And we have see interesting thing is that this seminar is very related to spectroscopy. Now, the question is that we can establish by this one, we can assume this one, but we cannot totally establish without single crystal X-ray diffraction. So, single crystal X-ray diffraction is very essential to establish this kind of structure, because your NMR mass can tell us about the possible structure, but they cannot tell about the geometry. And point is that to confirm the geometry and bonding connectivity, we take the help of the single crystal X-ray diffractor spectroscopy. Now, see what happened. So, look about these things. We have the tetranuclear silver, and we have this structure, single crystal X-ray structure. We have seen that 4 silver is present in the earth, and when we are selectively transmetallated, then it will look about these things. This is 2 gold coming to here, they are bonding with the carbon, but 2 silver they are bonded to the nitrogen. And interesting thing is that here also, if you given 4 equivalent of gold to substitute all the 4 silver, that is not substituted. It is selectively substituted only 2, not the 4. So, that is the beauty of this molecule. Anyway, so we take the help of the NMR. This is the ligand we have synthesized, and we have assumed this is the correct assignment. We have this proton appears near about 9.8 ppm, and when we make the complex, then this we look about this proton disappeared, and all the aromatic proton downfield shifted. So, that tells about the formation of the complex. So, now the question is that this also leads to another supramolecular architecture, because here we have silver and another molecule. Look about these things, these have a silver long interaction, and they can develop a 1D and 2D structure also. And same thing happen in case of gold also. Gold also. Now, the question is that we know that silver has the property for optoelectronic property, because they can absorb the light and they can transfer the electrons. So, we have to study the optoelectronic property. And another important thing is that we we have studied the luminescence, and this kind of silver and gold compound both are luminescence, and this luminescence arises we think about because of the silver interaction, and this is the steady state fluorescence spectra, and we have seen that we have compared the silver compound and mixed metal silver gold compound, and we have seen that the solely silver compound, they have much more electrical conductivity than that of the silver gold mixed metal complexes. So fine. Interesting thing is that if you look about this earlier molecule, we don't have methyl group here. So we don't have methyl group here, so that is why we got this kind of rectangular structure, I mean grid-like rectangular structure. But now we try to see what happened if we substitute one hydrogen by one methyl group. So now look about this thing, simple one substitution of a methyl group, how it's a rectangular structure to it's come a linear structure. It's come a linear structure. And beauty is that in the linear structure, when we all the silver is present here, it is from a 1D structure, and when you try to substitute the silver by gold, you look about these things, all the silver is substituted by the gold. And earlier cases, you look about this, it was tetranuclear structure. I mean 4 center is the metal center is there, but in case of present, you look about the 3 center is there, and selectivity lost here. So this is the beauty, and point is that except single crystal X-ray spectroscopy, it is very difficult to establish this kind of structure. So only your mass and NMR cannot tell, they can tell about the bonding, but they cannot confirm about the geometry. So that is the beauty of this single crystal X-ray spectroscopy. Only fine. Now look about these things. We have this kind of linear structure. Point is that if you look about this molecule, there is the silver is bonded with, this is 1D structure. Silver is bonded with one nitrogen, one carbon, and same molecule give this dinuclear structure. So your NMR and mass cannot I mean confirm about this kind of geometry, because this is infinite linear chain, and this is defined the confined dinuclear structure. Only if you look about take the help of the X-ray crystallography, then we can confirm about this kind of structure. Okay, so this is the difference between the I mean earlier structure from this structure. Okay, fine. Yeah, we have confirmed this structure by single crystal X-ray topology, and look about these things. This is the graphical whatever is shown, that is confirmed by the gold. You look about these things. This gold is coordinated by 4 nitrogen, and this gold is I think bonded with this carbon. So this is we confirm by the single crystal X-ray structure. Fine. Now look at these things. We have discussing with this ligand having the PF6. Now we move to chloride ligand. I mean only the counter anion, main frame remains same, only we change the counter anion chloride. Now look about this, when you change the counter anion chloride and we treated the silver oxide. Now look about these things, what is the 1D, they are supramolecule they are developed, and here look about these things, this is chlorine beads, and this chlorine beads and silver is one bonded with carbon along with this nitrogen and along with these 2 chlorine. So this is a beautiful structure. So that is why we say there is an anion directed structural diversity. When we have the PF6, that is we have tetranuclear structure. When we have chloride, then this 1D linear structure they form. Okay, fine. Now thing is that earlier case you look about these things, we have nitrogen in the 3 positions. Now we have trying to develop the nitrogen in the 4 positions. So look about this. So nitrogen in the 4 position, and we have a, when we have a simple chloride anion, then look about these things, this is on ligand, this silver chloride simple structure is there. But when you transfer to a bromide, you look about this form a 2-dimensional structure, and there is a bridging bromide bond is there, and it is also very difficult to establish without single crystal X-ray diffraction study, because see this is 1D structure, linear simple molecule, but this is a supramolecule. So this is a beauty to take the help of the instrument XRD. Fine. Now we will move to another molecule, look about these things. Yeah, same structural diversity, how affect the things, we look about these things. We have this this ligand having the 2 position nitrogen is there, and when we have the chloride salt, we look about these things, thinking this silver bonded with 2 ligand, and there is because silver is +1, so this is AgCl2, this is silver chlorine, so AgCl2. So that is this is the neutral molecule, so Ag plus and AgCl2 minus, so they have this kind of structure. But when we take it the bromide salt, you look about complete different structure. So there is this AgBr2, and this nitrogen bonded with this silver, and that helps to develop the supramolecule. So, that is why it is a simple changing the anion from chloride to bromide, it is a huge change in structure and property also. Now we have designed some different kind of molecule, keeping see look at this simple organic ligand. Here there is two possibility. When one possibility when two carbon in a same direction, but there is some possibility also two carbon may be in the opposite direction. So, this is the same direction, this is in opposite direction. So, now by changing in the substitution, I will show how the chemistry changes. So, we have substituted this R group sometime with methyl, ethyl, benzyl like this and isopropyl like this one. So, see what the difference happen when we have the change the substitution. So, look at the things when we have this substitution R substitution ethyl, then two carbon centers should be in the opposite to each other. Look about this, they are opposite to each other. So, and this opposite to each other, and we have silver complex. Look about these things. This is the silver carbon bond in this direction, and this is the silver carbon bond in the opposite directions, and they will form a infinite chain having the supramolecule. Fine. No. Now look about these things. Now we substitute this nitrogen by ethyl group. Look about these things. Now the structures become dinuclear cyclic structure. So, that is why my point is that simple one substitution might have changed a lot of chemistry, and when we have this phenyl group, earlier the supramolecular I have shown that is developed. So, that is a huge change in chemistry by changing the substitution, counter anion, metal like this one. Now, I move to another interesting topic, tactons. So, this is tactons is nothing but this is the repetition of the unit. So, we are trying to develop some chemistry based on the tacton or some tactonic chemistry. So, now see what happened. So, look about these things. We have simple this kind of organic molecule, and when we have the chloride, look about this kind of structures developed where this silver is bonded with these two carbon, and in middle there should be AgCl2. So, silver is Ag plus and this is AgCl2 minus. So, that is a neutral. And look about these things, this form a 1D infinite chain, but supramolecular. But when we substitute by the when we have the counter anion bromide, look about these things, this form a tetranuclear silver structure having the bromide, but this is not the infinite change. Now, tacton is nothing but we say many of you aware of this tacton is nothing but this is repetition of the same unit. So, think about this is our carbon having the silver and two ligand, this is AgCl2. So, that is why look about these things is trying to develop one after having this kind of. So, this is a beauty of this molecule, okay, fine. And we have developed the single crystal structure also, look about these things, they have the things, okay, fine. Yeah. Now, the question is that we are trying to develop another kind of tactons, okay. Look about this beautiful chemistry. When we have this kind of ligand and we have developed silver chemistry, here trinuclear silver cluster is forming. And important thing is that earlier cases carbon is the only single donor, but carbon here acts as a bridging donor, okay, fine. You look about this carbon has a bridge between the two silver, and there is a silver trinuclear. So, this kind of cluster supramolecular form, this is fine, very interesting, and we have published this result in Dalton trans, fine. But my point is that we are looking about one nitrogen here. Now, we look about this, if you substitute, if you transfer another carbon by another nitrogen, see what happened. Really the chemistry will differ or even same like this one. So, graphically I have seen that will give a tactons, and that's give a very huge big molecule. I will show this one, this kind of graphically I have shown this one, and I will show the single crystal structure also, fine. So, and tactons I told you this is nothing but this is the repetition of the, yeah, I will take another 2-3 minutes, sir. Yeah, I will complete
8 minutes more.
Yeah, I will complete the stipulated time. So, look about these things, this kind of tactons, this is repeating, here they are repeating, this direction they are repeating. So, I am just showing for one directional, but this is not one direction, this might be a 3-dimensional structure. Look about this, yeah. So, look about this, graphically I have shown how, see, this is one unit, this is one unit, this is one unit, this is one. These 4 units they are arranged by one silver, and another things is that they are bridged by the 4 silver, this one. So, this is a very big molecule, and I do not know, I talk with my, my previous speaker Stephen is my friend, we are friends, so we talk about this. I don't know what happened. He told me, Joy, if you are able to study this one, look for at least nature chem or JAX or Angichem. So, that is I will see what happened. I keeping a good hope on this one, okay, fine. Yeah, so this is, see my point is that it is very difficult to establish this kind of structure with the simple help of NMR and mass, this kind of spectroscopy. only NMR mass helps me too much, but finally to know the structure single crystal X-ray structure is very rare. So we have developed the single crystals, and we have get the data. You look about this, is four center is there. This is one trinuclear, this is one trinuclear, this is one trinuclear, and in middle there is silver is there. So this is a rare organometallic tactons, because earlier lot of tactons is developed, mostly they are coordination compound, but very less example of tactons is there. So that is that we have developed in our laboratory in Utkal University. Now interesting thing is that many of you have looked about co-crystals. Co-crystal is nothing but we have trying to develop some supramolecular having the idea of co-crystal. So look about this simple molecule. We have this organic molecule when you have treated with silver salt. Then look about this molecule. This is a anion. This is an anion and this is a cation. So you know many of the students co-crystal is nothing but in a same set if you have a two type of crystal. So that is why I call co-crystal. So this is one crystal, this is another crystal. Look about the structure. This is one silver having the two ligand. This one silver two ligand, and that is the ligand AgBr and AgBr2 minus. Interesting thing is that we have read in the chemistry like potassium permanganate, potassium dichromate, they form the charge transfer spectra, and if you look about the UV spectroscopy, their absorbance appear in the longer wavelength. Yeah. So that is why we are hugely interested, because silver and one compound or this kind of compound didn't give the fluorescence in the longer wavelength. So now we are we try to find out. We argued this compound must have fluorescence in the longer wavelength, and that is we have proved. Look about these things. So this is the UV spectra of this compound ligand and silver compound, and they have absorbance near about 600 nanometer, and they are like a 350 nanometer. So when we look about the fluorescence, look about these things. This compound have a fluorescence near about 758 nanometer and 870 nanometer, means they are transferred to a near infrared NIR. So these are very important, and this property we have utilized for the cell sensing, because always we look about the we have synthesized the compound fine, but how we can use this compound. So now we have used this compound for cell sensing. Okay, look about these things, and this we have confocal microscopy in our university. So look about these things. We have taken the epithelial cell. When we treated this silver compound, firstly look about these things. The compound bind this cytoplasm. When time is passes, this is moved towards the nucleus, and within 24 hours it is totally transferred to nucleus. Look about these things. This is our compound. This is our dye from the market, and these are the mixed things. Mean our compound is there and market dye is there. So this compound sends the cells, and we are very sure this will be sends the cancer cell also, because we have some preliminary result, and this preliminary result tells about this also sends the cancer cell also. Fine, no problem. Now the question is that most of the cases inorganic complexes, they are interesting thing is that because of the presence of metal that become toxic, that kill the cell. That's very disadvantage to cell study. But point is that remember here we have the compound 0.1 micromolar, and they didn't kill the cell. Even though we move to here 1 micromolar, only maybe 5% cell killing. So that is why up to 48 hours they didn't kill the cell. So cell in living state and showing the emission, that is very important. So that is the beauty of this kind of study. Okay, fine, no problem. And we have the platinum compound. Look about these things. For this is nucleus. So you know everybody know the nucleus is. Look about these things very spherical. So that is they are sensing, and this is a very good result. And we have also and many of the students they can have the argue what is the importance of this study. Importance of the study is that look about these things. Sometimes it is very difficult to know the cytoplasm and nucleus. So here you look about just 1 minute. Look about it in nucleus and cytoplasm.
No,
point is, I finish. Just one slide is given. So when your nucleus become bigger, then cell we say is a malignant cell. So think about when you have a cancer cell when is a malignant state, the nucleus is bigger with respect to cytoplasm. So and a mature cell, nucleus is very smaller with respect to the cytoplasm. So that is why we try to understand the situation of the cell. So that kind of study not only can be used for the diagnostic purpose, but can be used for the therapeutic purpose. Okay. So this is the research we have done in our laboratory, and in conclusion we have synthesized several type of organometallic ligand. We have several complexes. We are characterized by IR, UVs, NMR, and finally by XRD, and selected complex we applied by the cell sensitive. Okay. Last of all, I am thanks to DST Government of India and Utkal University giving the opportunity, and IACS Kolkata, Cultivation of Kolkata, IICB Kolkata, Niger Bhubaneswar, my students, they did this work, and financial support from Department of Science and Technology, Government of India, and last of my students, they helped me a lot to develop this kind of chemistry. Okay, and thank you all for this kind of thing.
Thank you, for the fascinating talk. Very scintillating. Any question? The house is now open for discussion. Questions, please.
Basically, students side, if you have any question relating to supramolecular and organometallic.
Cordless.
Professor Dinda,
Sir.
can we replace silver or gold by copper?
Yeah, obviously. Yeah, we can replace by silver by copper. That's obviously.
But you have not given such things.
No, sir. In our lab, because when we did the silver on chemistry, we need the completely, better dry and nitrogen atmosphere. We have some things, but I have not shown this slide. Lot of copper on chemistry we have did, and here it is possible.
I hope it will not be possible in case of copper because
No.
the size is very small.
I have cluster structure copper. I have not shown you. Yeah, cluster structure. Yeah.
I have a question for you.
Sir,
Uh,
for anyone.
when Professor, when you are having a salt, N is carrying a plus charge.
Sir.
Am I audible?
Yes.
If N is carrying a plus charge,
Yeah.
it seems that basicity is lost, almost lost.
Yeah.
Then how the nitrogen metal ligation, bonding is happening? And what about if that is aromaticity? What about the pi acceptor property that you have studied? Say it is a loose kind of bond, and you have used the bonding word very loosely, as I understand.
Yeah.
Very loosely, have not established whether it is a real covalent or what is the polar character. It's fantastic. But where is the hydrogen going? What is the hydrogen going? You are missing out the hydrogen peak in the PMR.
Oh yeah. So I think I have not shown that. Yeah.
In
Sir.
the meanwhile, I have,
Yeah, sir. Yes.
I have
So I
thrown
am
two
sorry.
questions.
No, yeah, very valid question, sir. Look about these things, sir. Here we have the hydrogen. This is acidic hydrogen. What you would say, acidic hydrogen. We have used, and this is most acidic hydrogen here. And we have used the silver oxide. Silver oxide function as a base. So simple as a acid-base reaction, and from here, from the silver oxide oxygen, they are transferred to water. So that is why in this kind of reaction, to keep this organometallic compound safe, we have to abstract the water, so this compound can remain year afterward without any disturbance. Okay.
What about bonding, the pi acceptor?
Yes, fine. So
Because
point
there
is
is
that
a lot of pi bonding there.
yes, sir. So my point is that when some metal is bonded with this carbon, so my point is that aromaticity enhances. And this aromaticity, because that is proved by anyone, sir. Most of the aromatic protons.
Have you done the nitrogen 15 NMR when to establish the nitrogen link?
No, still now, sir. We didn't did
But you
it.
have shown beautifully carbon link as well as nitrogen link.
Yes.
Am I correct?
Yeah. Most of the cases we did these things judiciously. We have designed this ligand to develop this kind of supramolecular chemistry because
You have a
when-
nitrogen 15 probe in your university or somewhere?
Sir, we don't have any more. In university, we take the help of Niger and other to develop. We don't have XRD. So 99% research. So we take the help of our several friends, several collaborators to develop this kind of beautiful chemistry.
Thank you very much for the fascinating talk.
Okay, thank you, sir. Thank you.
Thank you, sir, for joining us today. making spectroscopy so relevant and applicable to the real-world scenarios. Now I would like to invite the chairperson, Sudhanshu Sekhar Tripathi, the convener, Professor Dr. Deepa Nag, and the organizing secretary, Professor Dr. Abani Kumar Sau, to felicitate Dr. Jaydev Dinda. Please give a huge round of applause.
Because this is very related to your syllabus. We have chemistry, third semester, fourth semester, we have exactly this syllabus we have. So, molecular chemistry and biochemical chemistry is there. And thanks to Sir, thank you. Thank you, madam. Thank you, sir. Thank you, organizer. Oh, yes, yes, fine, doctor. Thank you, thank you, thank you.
Thank you. Every spectroscopy is the fingerprint of the nature's truth. With this, now let's know about our next speaker, Dr. Bankim Chandra Tripathi.
Dr. Bankim Chandra Tripathi is Chief Scientist of the Hydro, Bio and Electrometallurgy Department at the Council of the Scientific and Industrial Research Institute of Minerals and Materials Technology and a professor in the Faculty of Chemical Sciences at Academy of Scientific and Innovative Research. He has enriched his career with research experiences across the globe, including postdoctoral work in Australia and South Africa. Dr. Tripathi's research and innovation record includes more than 150 publications, 4 national and 2 international patents, 6 book chapters and 1 book. In recognition of his work, he has the Sir C.V. Raman Fellow Visiting Professor in 2015 at the University of British Columbia, Vancouver, Canada. He received the NRDC National Meritorious Invention Award in 2019 under the category of National Societal Innovation for his work on hazardous waste aluminum truss, an honor accompanied by a citation. So please join us in inviting to Dr. Bankim Chandra Tripathi to enlighten us with today's presentation.
All the best, Dr. Tripathi.
Thank you for giving a very big introduction about me. So, with the permission of chair, let me present my talk. So, good afternoon to you everyone. And I must thank the organizer, Professor Sau, Deepa ma'am and the whole team for inviting me to share my work in this August gathering. And I'm sure this, my presentation will give a bit of different flavor than the other presentations. Basically, my work, what I'm doing is mostly on waste recycling. And here I'm trying to show how, with the help of different characterization techniques, we are able to produce very good we are able to justify the production of valuable materials and even metals from various wastes available in Odisha. So my topic is sustainable synthesis of functional materials by efficient resource utilization and waste recycling. So efficient resource utilization and waste recycling both go together. The thing is that once we need to we understand what is the importance of efficient resource utilization, then we can understand what is waste recycling. Okay, so to start with, I will give this: nature protects if she is protected. Friends, this photo which suggests, honestly guys, I am not a crow, I just arrived from Delhi. I am sure you have understood everything what the picture wants to tell you or give the information to you. It emphasizes the symbolic. Yeah, am I audible? Yeah. So you see that nature protects if she is protected. This emphasizes the symbiotic relationship between humanity and the nature. The health and stability of human life are directly connected to the well-being of nature. When we safeguard natural resources, ecosystems and biodiversity, nature in return sustains us by providing clean air, fresh water, fertile soil, climate regulation and disaster resilience. This concept serves as a reminder that environmental stewardship is not just an ethical responsibility, but a practical necessity for ensuring our own survival and the quality of life. Hope you all agree with me. So to have the introduction like this, because we are dealing with a lot of waste in the society, in the environment. So unless and until we take care of the waste, it's very difficult for us to have a healthy and happy life, because these wastes will ultimately give us so many problems in future that we have to deal with our life in medical only. Okay, and to get rid of those problems, we need to take care of the nature, we need to take care of the biodiversity, we need to take care of our environment. So in a world where over 2 billion tons of waste are generated every year, most of it ends up in landfills, polluting our oceans, poisoning our soil and accelerating climate change. Improper disposal of these wastes cause adverse effect on the environment and the biodiversity. This has attracted the attention of many researchers to focus on judicious use of resources and adopt recycling practices. Functional materials derived from the recycling of industrial waste play a crucial role in sustainable development, especially within the framework of circular economy. The circular economy focuses on reducing waste, reusing materials and recycling byproducts, thereby minimizing the consumption of the finite resources and reducing environmental impact. So friends, that we need to, there are two buzzwords are going on, like circular economy and resource efficiency, and the government is also proactive on this, that how these things can be taken care of and the society, the environment can be kept at place. So, these are some other points, and the mention is that my mention is that waste is not just a problem, it's an opportunity for recyclers. Who are the recyclers? We all are recyclers. The thing is that unless and until we take care of the waste, we take care of the little resources which are available, rather than concentrating on resources which are having very high concentration of metals and materials, then it will be a problem for us in future to deal with all these wastes. So, what is circular economy model? An economic system based on the reuse and regeneration of materials or products, especially as a means of continuing production in a sustainable or environmentally friendly way. That is circular economy, and we need to understand this, what is the importance of circular economy in the present context. What is capacity building? Capacity building is the process of improving the abilities of a person, group, organization, or you can say institute or the system to perform better. So, you need to have better capacity to deal with all the menace whatever is there in our surroundings. It can also be described as the process of developing the resources needed to adapt, survive and thrive in the changing world. So, for this we need to have better resource efficiency. Unless we improve our resources, we have to deal with these problems in a very bigger way. So, these are the 6 R principles which are key to drive resource efficiency and circular economy. So, many of you might be knowing, but just to tell you again that we need to deal with various waste, various materials in the universe. By this way, we need to use less of the material, we need to use the material till the end of life of the different consumers, then recycle, use the waste scrap to produce another useful material, that is what usually recyclers do. Then refurbish, restoration of the used product, making minor alternation, redesign, new design for minimum use of resource material, remanufacture, rebuilding a new product using reused and repaired materials. So, by this way only we can take care of the environment, or else we have to suffer a lot. So, for all these things we need to have a better technology. So, unless and until we develop a better technology which will safeguard the environment, it will be again a problem. So, the technology should be such that it should continue for longer time. You can you might be knowing about the Hall Herold's process, where aluminum metal is being produced, and this is a 200 years old technology, but still in the present context this is very important, because we do not have any alternative technology. So, our technology should be such that it should continue for a longer time, and also it should be cost effective, because unless it is cost effective, the way we are trying to manage the resources, it will be very difficult on our part to continue with that. So, the technology should be like this, it must aim at converting a hazardous waste to end of waste, justifying circular economy. So, our technology should be such that it should also take care of the environment. So, these 12 principles of green chemistry is basically very helpful for achieving these sustainable goals, which is the present day call. So, what I will do, I will just give some case studies where I have worked on different wastes or low grade resources to produce valuable materials for our day to day life. So, one of them is waste aluminum dross. So, you might be knowing there are a lot of aluminum industries in Odisha, and we have also very good amount of aluminum ores in Odisha. But the thing is that once the waste is generated, we need to tackle the waste properly, otherwise this waste will also help us in having a very bad environment, which will pollute the environment, which will pollute the soil, which will pollute the water. So, it will be in future. Now, at the moment we may not see the gravity of this situation, but in future this will be a very big problem. So, that is why we decided to work on this, and this was a problem with aluminum industries. This waste is generated during the production of aluminum metal, and so this is the aluminum dross, and this contains, these are the impurities. Okay. So, we have developed a patent on this in 2012, and based on that patent we had a recycler who purchased the patent, and he had this plant in Khurda. It is a first plant in India which uses aluminum dross residue to produce alum. So, this plant has got 20 ton per day production capacity, 20 ton per day alum production capacity from aluminum dross. These are the alum powders which are made from aluminum dross. These are crystalline and alum blocks we also produce, and these are the alum, high quality alum crystals we produce from aluminum dross. However, apart from that, we also did some work on having a zero waste process for aluminum dross treatment. Okay. This is this is the process which was adopted by Central Pollution Control Board as SOP for treating aluminum dross. That is another process where we have a zero waste process, where we produced basically aluminum hydroxide, from where we produced alumina through calcination. Also, we had produced the raw salt materials which are used in as flux in melting of aluminum metal. So, this is the process where we started with aluminum dross residue, and we produced alumina through aluminum hydroxide and salt, and also this residue, this is also used for as filler materials, or we can prepare some, we have prepared some refractory materials from this material. So, you can see it is a complete utilization of the residue. You can see the aluminum hydroxide which we produced has got very good crystal structure, and is also similar to, is at par with the synthetically prepared aluminum hydroxide which is available in the market. This is aluminum oxide which we made it from aluminum hydroxide. This is also equivalent to the synthetically prepared material which is available in the market. We use this aluminum dross also to make some artifacts for ceramic and refractory applications. And you can see when we treated these materials at a higher temperature, we got very good refractory materials and ceramic materials. Sir, I just want to say that this crucible, if anybody is using in the lab for high temperature calcination process or roasting process, this we have made it from the residue aluminum dross, basically having lot of alumina in it. This, when it is available in the market, you can get 2000 rupees one crucible, you will get in 2000 rupees. But when we are making it from this residue, the cost comes down to 200 rupees, sir. And this can sustain up to 1200 degrees centigrade, 1400 degrees centigrade, and we are using in our lab also, using this for high temperature applications. One more thing is this is another low grade resource, is where we have produced very good energy materials. This is production of manganese sulphate and energy efficient materials from lean grade manganese ores. This is the lean grade ores which is dumped near the mine sites. Once they take out the high grade ores, what they do, which are low grade ores, they dump in the near the mine site. However, there are plenty of these materials available, almost million tons And one of the recycler, they approached us and told that if you can do something, but we are not able to at the moment we have not gone up to pilot scale applications, but we have done it at laboratory scale, but also we have prepared in bench scale also. So, this is the process where we have prepared this manganese sulphate, which is the precursor materials for manganese sulphide. So, we first prepared manganese sulphate from this ore, and then we got manganese sulphide. So, this is the way we started with low grade manganese ore, and we reached at cuboidal manganese sulphide nanostructures, which is a very good material, very good electrocatalyst for OER. So, this is very good cuboidal morphology which we had, and we can see through X-ray diffraction studies and Raman spectroscopy we justified that the material which produced is a very pure and nano characteristics, having nano characteristics. Also from EDAX we found that the material is very pure, and with the EPMA also we found that this is purely manganese and sulphide. So, TM also justified our findings, and we did some electrochemical studies to justify that it is working as a very good electrode catalyst for oxygen evolution reactions. The other one is zeolite from waste aluminum dross and rice husk ash. We produced very good quality of zeolite using this aluminum dross residue and rice husk ash. So, you can see the demand of zeolite is very high, okay. And also at the same time you will see that we have being in Odisha, we have lot of because we are a rice prone area, we produce lot of rice here in Odisha, and we have got lot of rice husk also, which contains silica basically. So, what we have done, this is the waste rice husk. See, in what happens in Odisha, it produces 2.4 million tons of rice husk annually. Currently, on a very small fraction is recycled. In fact, most of them are being used in burning inefficiently in rice mills, dumping or burning in open air. You might have heard about the news also. We have enough raw materials in districts like Bargarh, Kalahandi, Balangir, Sambalpur, Mayurbhanj, and from this rice husk we are able to produce these materials which are very useful, and in fact we produced very good quality of silica out of rice husk. The silica was 99.5% pure, and also we produced silica gel, we produced silica alkogel, and we produced sodium silicate, which is a day to day requirement for all the refractory industries. So, this is the way which we produced, by where we produced. Then what we did, we took this aluminum hydroxide, which we made it from aluminum dross, we made sodium aluminate liquor from there, and then we add this silica from rice husk, and we produced very good quality of zeolite from this material. So, these are the two processes where we produced sodium aluminate liquor and also sodium silicate, okay, and then we mixed them. This is the way where we produced zeolite, and we tested the zeolite quality through various characterization techniques. One of them is X-ray diffraction, and we found that this is a very good way of utilizing two wastes and making a very valuable product, which is very important nowadays. And it's you might be knowing that zeolite is very useful for day to day industrial purification of various gases and liquids. So, for take home messages are: sustainable development means building a better future by balancing technology, the environment and the society. We can turn waste into valuable products, from clean energy to eco-friendly materials, making us the key players in creating a more sustainable world. every plastic bottle reused, every circuit board, electronic circuit board recycled, every waste stream reimagined is a step toward a more sustainable planet. We are not just solving today's problem, we are creating tomorrow's possibility. So, let us be bold, let us be innovative, let us be the change makers the world needs. Be the recycler who transforms problems into possibilities and waste into wealth. Turn trash into treasure. So, thank you everyone for listening to this patiently. So, now if you have any question, please.
Let me first congratulate you,
Thank you, sir.
because you are the first person till now
Sir.
who has completed before time.
Oh, because I have less number of slides.
You know, exciting moment for all of us. Questions
you.
from all of you.
Nice talk. So, has anybody done the spectroscopy of those silica derived from rice and
We only did Raman,
no other spectroscopy?
XRD. No, no. Because we are developing this process for a industry. So, industry does not need this high, but when we will go for making silicon metal or silicon wafers from this silica, because till now we have gone up to silicon carbide, till now industry is satisfied with these products. But when we will go for silicon metal, because that time we need very high purity, 4N, 5N, 6N, 7N purity, that time we need to have very means lot of characterization techniques to justify that this is 6N purity or 7 purity. And also silicon wafers, for that we also need lot of more technologies, characterization techniques basically. But for this, as far as industrial product is concerned, because in industry they do not need very high pure, they need only to sustain and recycle the material for their day to day use, because this silica they can be easily used in refractories, easily used in your ceramics, not a problem. When you think of making high grade silicon wafers, then only the purity is very important.
It may not be cost effective also when
Yes,
you
yes.
convert it to high grade, semiconducting grade.
No,
do you think?
the process itself is very costly, sir, but the product is also costly, sir. Silicon wafer 1 kilo is some almost 20-30 lakhs, if I remember correctly. So, it depends on the product quality also.
Professor Biswal, any follow-up question you wanted to suggest?
No, that's fine. I'll take their silicon do spectroscopy. That's it. I'll call it from you.
Sure, no problem. In fact, now we are preparing.
Good afternoon, sir. So I want to ask you, what is the cost effectiveness of conversion of rice husk to zeolite?
Zeolite?
Yes, you told that we can convert rice husk by methods into zeolites. So what is the cost?
Rice husk and aluminium dross.
Yes.
Together.
Because both are waste. I will say, but I will not guarantee at the moment. We have gone up to 100 gram scale, 100 gram scale.
Yes.
But we are still on the process of making it to higher scale, like 1 kg scale, 10 kg scale. Then at that point of time, cost will be an important issue. But at the moment, it is not very costly, but it's not very cheap also. Because we are dealing with some of the chemicals, we are dealing with synthetic chemicals. But when we will do in pilot scale or industrial scale, we only use industrial chemicals, not synthetic chemicals.
So it is lack of awareness among common masses. For that reason, we cannot convert more rice husk to zeolites, or what is the cause?
No, that is the reason only, because many people they do not know that we can use these rice husk in making very good zeolites. Actually, this concept came when a student came and did his master's training course from CPET. So, I told, why don't you try this, and it beautifully worked out, and he got the first in CPET. So the concept was very good, and we could able to produce it in
Tripathi,
a.
what is CPET to do with silica? They are working on silica.
No sir, CPET are dealing with the plastic materials, but they have summer projects, summer. So they came to me to do some work. I told they want to basically use recycling materials, waste basically. So I told these are the waste available with me, you can try. So and he tried and he was successful.
Thank you, sir. Thank you, sir.
If you have no other question, then thank you,
Thank you, sir.
Dr. Tripathi,
Thank you,
for
thank
your
you.
excellent talk.
Thank you sir.
Thank you, Dr. Tripathi, for your insightful presentation on transforming industrial and agricultural waste into variable functional materials. We deeply appreciate your valuable contribution. Now, I would like to request our chairperson, Professor Dr. Sudhanshu Sekhar Tripathi, the convener, Professor Dr. Deepa Nag, and the organizing secretary, Professor Dr. Abani Kumar Sahu, to kindly felicitate Dr. Bankim Chandra Tripathi. Please join me in applauding. Thank you. We now move on to our next distinguished speaker, Mr. Balogo Io Felix.
Mr. Felix is a lecturer and examination officer in the. I guess.
Friends, let me tell you that Mr. Io Felix Balogon and Mr. Bertrand, and they are from Io is from Nigeria. He is working for his PhD degree with me under TUAS fellowship, and Mr. Bertrand is also working for his PhD with another colleague of mine at IMMT, and he is from Benin, West Africa. So because they were here and Abani sir was kind enough to invite them, so I told them to accompany me, and that's the platform where they can share their work, what they have done, they are doing at IMMT. Thank you.
Good afternoon, everybody. I'm very happy to be here. Thank you, the principal and the organizing secretary, for inviting me. And I won't be here without the support of my guide, Professor Bankim Tripathi. So I'll be presenting a topic on preparations of bismuth oxychloride from bismuthite ore, and I'll be testing it as an electrode material for spark capacitor application. Sorry. And this is the outline. I'll talk about Nigeria. Nigeria is one of the African richest countries in terms of mineral resources. And this is the map of Nigeria showing each available resources in each of the states. Introduction. Bismuth is a valuable and strategic metal which belongs to the group of chalcophilic elements. Its closest analogy are antimony and lead. As a rare heavy metal with larger density and low melting point, bismuth is on as green metal due to its no toxicity, and that has necessitated its use in numerous applications. Bismuth is mainly extracted from two kinds of material. One is from the raw ore, and the other is byproduct processes from extractions of either copper, zinc, and lead. These are the different types of ore bismuth that are available. And the first three cells are the most common. That is the carbonate types, the sulfide types, and the oxide type. And these are the physical properties of bismuth. And one of the unique properties that makes it to find unique applications in some of its uses is the low melting point, which is 270 degrees Celsius, and also its density at 9.2. These are some of the reactions that bismuth that go when it reacts with either acid or base. According to the United States Geological Survey, bismuth is very rare. So it's estimated to be around 370,000 metric tons, and China has the highest reserve as 240,000 metric tons. Due to the increase in environmental regulation, has necessitated the use of bismuthite to substitute some metals that are toxic, and that has increased the productions and consumptions of bismuthite. And these are the applications of the compounds that are being produced from either bismuth materials. It's used in medical line as antimicrobial. It's also used as sensors, as water purifications, as photocatalytic degradations, and also as electrode material in supercapacitor. And this scheme is showing the development process of bismuth-based material in energy storage and in electrochemical separation. These are the conventional methods that are available in processing of bismuth-based material. We have pyrometallurgy, hydrometallurgy, and we have the use of non-aqueous solutions, the use of microorganisms, to leach, and the use of electric energy charge to lose. But in this process, what I use is hydrometallurgy, which involves leaching and precipitation. These are some of the works that have been done on bismuth-contained materials. And my aim is to prepare bismuth oxychloride from a bismuth material and explore its potential applications in energy storage technology as supercapacitor. And in order to do that, my objective is to carry out a detailed characterizations using SRD, SRF, and SEM, and also ICPOES, and also to investigate the leaching kinetics of the bismuth ore in hydrochloric acid, and possible precipitate a compound, and also apply it as a negative material in energy storage. And these are the processes, experimental process. The ore was pulverized and shifted into different particle sizes, and these are the characterizations that was used. The physical study was done to determine the pH, and so the moisture content and loss of mass of ingredient. So this is the leaching procedure. The leaching procedure was carried out in a laboratory scale where we make use of beaker. 500 ml beaker was used, and on a hot plate, it was equipped with mechanical stirrer and thermometer to regulate the temperature, where we will put the leaching agent, which is the hydrochloric acid, in it, then heat to the required temperature. When we heat to the required, we now have 10 grams of bismuth chloride. At the end of the reaction, the solution was filtered, and the residue was thoroughly washed and dry and also characterized. This is the analysis, elemental analysis done using SRF and ICPOS. It shows that the material is rich in bismuth, and these are also other impurities that are there. There is the SRD characterization that shows that the material is bismuthite, and it also contains zinc diet and quartz. And the same analysis also supports the SRD. This is the leaching studies, the effect of temperature, the effect of concentration, temperature, and particle size. And under optimized condition, I'll be able to achieve the leaching efficiency of 98%. And in order to gain insight into the leaching kinetics, the cyclical model was applied to the leaching. The experimental data experimental data obtained from the leaching studies. And this is the graph to demonstrate that it followed diffusion control mechanisms. The leach residue was also characterized to know the amount of the bismuth that is still left after leaching, and it shows that from 78%, we only have 1% left. And this is the SRD analysis of the residual product, shows that the bismuth has been leached out of the ore. We now have quartz and aluminum. So the stock solution, from the stock solution, 200 ml was taken, and sodium hydroxide was used to adjust the pH in order to precipitate bismuth oxychloride, and this is the process head, and this is the powder that was precipitated at the pH of 7. And this is the SRD result to show that the compound precipitated was actually bismuth oxychloride, and this is also the same result. So there is the electrochemical properties of the bismuth oxychloride that was prepared, and it was carried out in 3 electrode systems. And this is the CV, the GCCD, and the EIS. And it shows that the material is shows a good property. That's a good specific capacity property of current density of 1 gram ampere. It shows that the specific capacity is 257.9 Faraday per gram. In conclusions, we're able to carry out the mineral characteristics of the ore, and the leaching studies shows that 98% of bismuth has been leached. Also, the kinetic analysis shows that it followed the diffusion control mechanism, and the compound prepared was bismuth oxychloride, and we're able to demonstrate its potential as negative electrode for supercapacitor application. I want to thank my guide, Professor Bankim, for his support in my stay in India, also CSRR, TIWAS for financial support, and all the friends. Thank you for listening.
Thank you, Mr. Felix, for your excellent talk. Any question? So, can you please tell me that in the bismuthite, is it a stoichiometric compound, or it's a non-stoichiometric one? Have you established its stoichiometry?
No.
Bismuth is in which oxidation state?
+3.
+3. Thank you.
How are you maintaining the pH of the solution? pH, yes. How are you maintaining? It means generally the acidic medium you have done, all the putting methods. Acidic medium or basic medium?
Are you talking about the precipitation of the compounds, or what?
Yeah. The electrolyte solution, you have taken the electrolytic solution. No? So how can you maintaining the pH?
I don't understand what you are saying. I don't understand your question.
Are you using a buffer solution or something
For
maintaining the pH?
For the leaching process or what?
For electrolytic process. Electrolytic process.
That's
for the preparation of chemicals, sir.
Preparation of chemicals?
For the preparation of chemical, how can you maintain the pH?
For the preparation of the compound?
Yeah.
I told you earlier that I use sodium hydroxide to maintain the pH.
Okay.
Yes.
Thank you.
Thank you.
Thank you, sir, for your enlightening presentation on the development of the high purity bismuth oxychloride and its application in next generation technologies. Now I invite the chairperson Sudhanshu Sekhar Tripathi, the convener Professor Dr. Deepa Nag, and the organizing secretary Professor Dr. Abani Kumar Sahu to felicitate Balagan. Thank you. Spectroscopy is the language of the universe, revealing the secrets of matter and energy. Now let's move to our next speaker, Mr. Bertrand Anagonov.
Mr. Bertrand Anagonov completed his BSc in Applied Geosciences, Mines and Petroleum at the University of Abomey-Calavi, Republic of Benin in 2016, and his MSc in Mineral Exploration Geosciences at the Pan-African University, University of Ibadan, Nigeria in 2019. He joined Council of Scientific and Industrial Research, Institute of Minerals and Material Technology, Bhubaneswar in December 2022. After qualifying for a CSIR UNESCO TWAS Fellowship to pursue his PhD under Dr. Bibhuranjan Naik, Chief Scientist and Head of the Mineralogy and Material Characterization Department, Bertrand has served as an assistant lecturer at the University of Abomey-Calavi since 2020. He has authored 5 scientific papers and presented his research at several national and international conferences. His research interests include mineral exploration and ore geology. So let's join us in giving a hearty welcome to Mr. Anagonov to the stage.
Okay. Greeting to everyone. My name is Bertrand Anagonov. I'm from Benin Republic, West Africa. So today I'm taking you guys to Africa. We have been hearing from India everywhere, but now I'm taking you guys to Africa. First, with the permission of the audience, I would like to thank Professor Bankim for allowing me to be here to discover Kotak. It's like he loves Kotak more than MMT India. I don't know why. I was there last week. He called me, Bertrand, there's one conference in Kotak. I've been in Bhubaneswar since almost 3 years, but I did not heard about Kotak. But last week he said there's one conference in Kotak and you must go. I don't know why he loved this college like that. Maybe he was graduated from here. So you help me to thank him for helping me to discover Kotak. Thank you to everyone. And for the presentation, you may not please mind my English. The accent will be different because I'm French speaker. So, but I will try to make myself understandable. Okay. First, I'm working on gold. I did my BSc from Benin Republic in mine and petroleum. My MSc from Nigeria. Then my PhD here, I'm working on gold in CSI MMT under Dr. Bibhuranjan Naik. The topic on which I'm going to present now is grade and purity assessment of gold in the Pema area, Republic of Benin, West Africa, using advanced characterization method, including ICPOES and ICPMS. As I was saying, I'm taking you guys to Africa. This is my country, the yellow part. The pointer is not working. Oh la la. This is my country, and this is the African continent. We are located on the western part of Africa, and this is the flag of my country. From here, you can see the area view of the country. And those are the famous statues in the country. You can Google it. Then come back to our topic. As I was saying, I'm trying to make friends with gold. So gold, as you know, gold is a high value and critical metal In the year 20, gold price was 10,000 euro per kg, but in 2025, you can see gold price has increased to 7,000 euro per kg. Gold is used in many domains like jewelry, coins, electronics domain, and others. On the world scenario, the 5 world gold producer countries are leading by China, followed by Russia, Australia, Canada, and USA. Among all those countries, none of African countries are there. But every time we are talking about gold on the African continent. Going back to the African continent, the 5 top gold producers countries are leading by Ghana, followed by South Africa, Mali, Burkina Faso, and Sudan. As you can see from the map there, oh la la. This is the African continent, and this is my country. Here you can see the gold producers country on the African continent. As I was saying, among all 5 top gold countries, gold producers, my country was not part of it. But in the country we are talking about gold all the time also. So gold has been mining in the country since 19 to date, and gold occurs as primary gold and secondary gold, but little is known about the gold. If you allow me, I will just explain a bit about how they are extracting gold artisanally in the country. So I did my field work and brought the sample to India. So from here, as you can see on this image, on the field, they will just go and settle down there, then collect the sand, wash it. Then at the end, by washing, they used to put some blankets here, and gold is a heavy metal. By washing, it will not go away. It will be trapped within the blanket. Then at the end, they will just take the blanket and shake it, then collect the gold grain. Also during the field work, as the rocks, they are too hard, only strong people, they can hammer it and reduce it in powder. So for those those that have financial means, they are bringing some equipment, machine to grind the stone, then reduce it in powder. Here is corn flour machine, but they are using it to grind stone. So at the end, they will get the powder. Then from here, they will wash the powder now. At the end, they will collect the gold grain. But during the field work, we can get some nugget of gold in the area also. At the end of the washing process, if they finish washing, they will get the gold grains like this, but they use mercury solution then to aggregate the gold grain, and this is what we are seeing in there. So coming to the geological setting, my study area fall within the Pan-African orogenic bed, and the bed was formed from the collision between the West African craton and the Benino-Nigerian basement bed. And the bed is made of 3 parts. The main part is the external unit, which is this one. Then the external unit, in between we have the suture zone. The external zone is made of much of rock type, as you can see from here: conglomerate, shale, sandstone, limestone, gneiss, and amphibolites. The internal zone are made of granulite, orthogneiss, and much of rock type, as you can see from here. Sorry, the pointer is not working. You can see this is the external part. Then the suture zone is made of those type of rock in the area. This is the sampling map and the rock type we collected from the area. The image A is gneiss, the B is amphibolites, the C is quartzite, then the D is active gold pit. And here is, I'm here with my co-supervisor during the field work. Then also the rock type in the area, we can see some exudation quartz vein and some pyrite grain are visible in the rock within the area. Here also you can see the exudation quartz. Maybe later we talk about how those quartz veins were formed. And here you can see gold grain and the nugget gold we are getting from the area. This is stereo microscope view of the gold grain here when I'm doing the laboratory check. And going for mineralogical study, I carried out inside the analysis after optical microscope checking. Then the mineral we are able to identify in the rock. From the auto-gneiss, we are able to identify quartz, muscovite, microcline, albite, biotite, auto-gneiss, and hematites. Furthermore, I went for ACM for the auto-gneiss. Then we discover much of minerals in the sample, as you can see from there, from quartz to monazite. For the amphibolite, same thing. With inside the optical microscope, and we are able to identify quartz, tremolite, arsenolite, epistene, unblend, epidot, rutile. The same rock type we went for ACM with it for further analysis, but we discover much of minerals in the rock type, as you can see from there, from quartz to gold. Here we were able to identify gold in the rock. From here you can see. Then with the quartzite, there are two types in the study area. But the first one is this one, massive quartzite. The second one is quartz muscovite schist. The difference between them is the amount of muscovite in the rock. Otherwise, they are almost the same, and they do not contain much of mineral. We got only quartz, muscovite, hematite, and rutile in those type of rock. With ACM analysis, we discover quartz, muscovite, autoclase, hematite, to zircon. But here we could not identify gold in the sample, but during the field work, we were able to identify gold, as you can see from here. Then coming to mica schist rock type, we identify under an optical microscope quartz, muscovite, hematite, magnetite, zircon, and pyrrhop. With ACM, we discover much mineral, again, like you can see from here, from quartz to gold. And here we were able to identify gold in this sample. And there I can just explain how the exudation quartz I was talking about was formed. This is the exudation quartz, and they are metamorphic quartz. How they were formed is during the metamorphism, when the temperature increases, the host rock, they lose water, the watering. Then the water at the end of metamorphism process, those water will crystallize.
Mr. Bertrand,
Yep.
How long you want to take, as per your estimation?
No,
How long?
5 minutes I will finish.
Yes,
Not
please,
much.
please finish in 5 minutes.
Yeah,
Okay.
no
Thank
problem.
you.
I will finish. Okay. With the quartz vein, those are the images, and under optical microscope, we are able to identify quartz, autoclaves, muscovite, epidote, silver, gold, and chalcopyrite. With the same sample, we did ACM, and those are the minerals we are able to identify from the sample. With SRF, for major element, but at that level, we were able to identify in one sample the mica schist, gold, as you can see from here, 0.041 weight percentage in the mica schist. With ICPOES, you can see the grade of gold vary from 8 to 98. The minimum we are able to identify is 8, and the maximum is 85. So with that one, we did EPMA to assess the purity of the gold. And with EPMA, we were able to identify that the purity of the gold varied from 91.38 to 93.10. And according to the classification, the pure gold ranking is 24 carat. Then the study gold fall within 22 carat from here. So it's contain 91.6 and above. From there, we want to use ICPMS to confirm the result we are getting, and we use fire assay to extract the gold. From here, we collect the sample, then mix with some chemical, then put it under a furnace and increase the temperature to 1050. From here, then let it for 2 hours, then it will make a melt like magma on the field. Then at the end, we let it cool down, and we extract the gold, as you can see from here. And from this one, we will make the solution of that one and go for ICPMS. So in conclusion, we can see load and disseminated gold occur in the massive quartzite, quartz muscovite schist, mica schist, quartz vein, and amphibolite and gneiss. And the gold grade vary from 8 to 98 ppm. The study gold purity is ranked between 22 carats, 91.838 to 93.10 on the international ranking markets. So we would like to thank the funding agencies, CSI UNESCO TWAS Fellowship, the director of CSI MMT, the staff and the workers of Mineralogy and Material Characterization Department, CSI MMT, all my lab mates, the PG Department of Chemistry, Stewart Science College, and the organizing committee of this international seminar. Thank you. Merci beaucoup. Merci beaucoup. Thank you for your attention. This is in French. Thank you.
Question, please. Mr. Bertrand.
Yeah, sorry.
So you guys must be here. This is Sudhanshu Tripathi. I'm speaking.
No, he's not there here for now. He's busy, but I'm here.
Huh.
Yeah.
So you guys must be very rich because you are mining gold from your backyard, I think.
Kind of.
Kind of. Yes, thank you.
Thank you, sir. Any other question? Oh, okay, thank you. Your mic?
Thank you, Mr. Button, for your insightful presentation. May I now invite our chairperson, Professor Dr. Sudhanshu Sekhar Tripathi, the convener, Professor Dr. Deepa Nag, and the organizing secretary, Professor Dr. Abani Kumar Sahu, to felicitate Mr. Button. Please give a big round of applause for Mr. Button.
Okay. After such inspiring discussion, it's the perfect time to recharge ourselves with a hearty lunch. We invite you all to the dining area and we will gather back here at 2:15 am sharp to continue with our seminar.
After the lunch.